Thank you, Alan. Ladies and gentlemen, it's a real privilege to be here, and I would like to thank the organizers for the invitation. I will be talking about global energy perspectives, and I think that fits really well to inspirational talk that Alexander just gave us. It is really about the innovations, institutional and technological innovations, and the need for a major transformation in the world. I have put as a subtitle, efficiency and decarbonization innovations. What I'm trying to say with that is we need to do more with less, and for that we need investments, and we need innovative ideas. For some reason, this is not, okay, there we go, I'm sorry. Let me just start by trying to frame the problems by mentioning the major challenges. Today, we have 7 billion people in the world, and 3 billion, which you might not know, you might not be familiar with, 3 billion of those people cook with solid fuels and suffer huge health and development barriers from that, and about 1.5 billion people do not have access to electricity. Now just think back, Industrial Revolution was mentioned. If you think back to 150 years ago, we had 1 billion people in the world, population increased by a factor of 7, global economic output by a factor of 100, and yet 3 billion, close to half of the people are excluded. Another way of looking at that is if we can connect this 3 billion, we'll be doubling the energy markets. That means huge demand for innovation. And efficiency and decarbonization, I will argue, are central. They bring multiple benefits for health, for security, and also for a long-term major challenge, which is global climate change. However, the financing requirements are huge, but I think they're doable with the right and sustained policies. Let me just mention immediately, we need to increase the investment in energy by about 50%, from about 1,300 billion today to almost 2,000 billion. This is the Global Energy Assessment. Here I have a physical volume that has been published with Cambridge University Press, but you can download it from the website above. The book involved 300 authors and 200 reviewers, and it's quite rich in material. It took 6 years to develop, so I'll just give you some glimpses into that. Let me start with this map of the world. In the color code, let me just explain the color code. If you go from green to red, this is the number of people who do not have access to modern cooking and who have to cook with solid fuels is increasing. I mentioned it's 3 billion altogether. The darker the color is, the darker the color is, the less access is. These are the 3 billion people, and going from green to red are the people who do not have the access to electricity. So if you look at the Nepal, North India, people cook with solid fuels and do not have access to electricity. Sub-Saharan Africa, about 750 million people live there who have to cook with the solid fuels. So this is a huge potential market. Our estimate is that it would cost about 40 billion per year for next 20 years to connect these people and double the energy markets worldwide. From that point of view, even though it's a huge amount of capital required, it's not large compared to the other international flows. So the first question that one might ask is, do we really have enough energy for all of these people that need to be connected? And now you know, of course, that renewable sun is huge. We can produce almost any amount of energy from sunlight, but we need new technologies, we need investments, and we need systems and infrastructures. But fossils are also large, so let me just give you a fossil picture, and I'll do it a little bit unconventionally. I'm showing you not energy, but how much carbon dioxide would be released if you would burn it. So the red square that you see up there is the conventional oil reserves. About 1,000 billion tons or gigatons of carbon would be released if you burn all of that. Then comes natural gas, another 500 billion tons, so together 1,500 billion tons. Then the biomass above the ground, all of the plants, is about the same amount of carbon. Unconventional oil, tar sands, is also the same magnitude. So all very huge numbers. And now, of course, being in Russia, the country with huge hydrocarbon resources, if you look in particular as unconventional natural gas, such as tight gas and gas shales, you can see that the amounts are truly gigantic. Even the lower estimate is truly gigantic. Coal, a very rich resource in Russia, is also huge. And then the gas hydrates, what I think in Russian is called the burning ice, could be as large as the whole screen. So the hydrocarbons are truly gigantic, and the problem is that we can emit only a small part of it, because if you see, our atmosphere contains 3,000 billion tons. And so even just burning conventional oil and gas will not do it. We will then go way above the 2 degrees. So the amount of carbon we can still emit is about 850 billion tons to stabilize at 2 degrees. So only a small fraction, unless we develop technologies that can separate carbon. And here you see 6 projects around the world, so-called carbon capture and storage projects, very difficult technology. We control it only at the pilot plant level. Would require huge investments and de-risking, because there are all sorts of risks involved with that. But imagine the possibilities if one could separate carbon from natural gas already in Siberia, store it underground, and bring clean electricity and clean hydrogen to the markets. That would be a big part of the solution, but it requires innovations. Another area of innovation is the cities. So we need large infrastructure systems to transport and bring the energy to the people. You have heard the notion of the smart systems, producing locally and coordinating it, but that's not enough for the urbanization world. Today, 3 billion people live in the cities. By the middle of the century, we expect that to double to 6 billion people. So it's a huge, huge challenge. And what you see here is an idea. You see the energy pipeline there, transporting either LNG, liquid natural gas, for example, from Siberia, or hydrogen, and in the middle is a superconducting cable, and next to it is a magnetic levitation train. These are the type of infrastructures we need to develop. Let me just illustrate that to you. This is an idea. Huge markets will be developing in Asia. You can see the idea of producing sunlight in the Gobi Desert, also local energy, and perhaps importing gas from East Siberia through this kind of supergrid that's connected to the smart grids. But that requires this huge investments that I've been talking about. Now, the Secretary General of UN, Ban Ki-moon, has put quite a big political weight behind the idea of sustainable energy for all. There are 3 goals: universal access, that's the 40 billion I talked about, doubling the energy efficiency, so doing more with less, and doubling the share of renewables. And for all of that, we need large systems. These are aspiration goals, but I think they're doable, and I want to show you an example. This is the global energy picture today. From the beginning of the Industrial Revolution, we need about 500 exajoules. That's about 12 billion tons of oil equivalent energy worldwide, and you can see that it's 80% fossil. Here is one scenario out of many that fulfills the Ban Ki-moon goals and stabilizes climate at 2 degrees. So it's a real challenging scenario. It's the one where we need a 50% increase in the investments and the new energy models for innovation. You can see that the efficiency improves by 40% by 2030. That's the white arrow. The renewables are about 30% in the energy mix. What is really important is, as you can see, that natural gas also has a fairly large share. Natural gas and renewables harmonize very well, because natural gas is a kind of a virtual storage. So when there is no sunlight or wind, you can use gas, and if you do it with carbon capture and storage, and that's a lot of that in this scenario, then it's also zero carbon. So that's the nature of the challenge that might be ahead of us. For that, we need vigorous technology development, and this is my penultimate slide. I would like to highlight this. These are so-called learning or experience curves. On the vertical scale, you have the unit costs in dollars or ruble per kilowatt installed capacity. On horizontal scale, the capacity itself. So you can see that photovoltaics costs have decreased by an order of magnitude, over 4 orders of magnitude of increase in the worldwide capacity. The middle curve is the wind, offshore wind, no significant improvements, and the red and the blue is nuclear in France and United States with cost increases. This is what we need to avoid, and that's why we need vigorous investment in innovation and the new technologies to avoid exactly that. So let me conclude by showing you the last presentation, the last slide. What you see on the vertical scale is percent of global economic output. And the first thing I'm showing you is how much we would need to invest in order to improve the security, about 0.2% of the global output. to reduce the air pollution about 0.5%, and to combat climate change to go to 2 degrees about 1%. But the key is, if we try to follow all of those goals at the same time by having a holistic innovation policy, then the marginal cost of doing all 3 goals would be only a tiny bit above what the climate alone would cost us. But that would bring huge benefits in the short run for security, energy security, for health. So we need holistic policies, in particular in the area of innovation. Thank you.